have seen in an earlier video, the very first stage is that of tokenization. And into the tokenization, if you like, layer of processing is, definitely consists of two discussions. One is really what today's tokenizers are doing, and the second discussion is why they're doing what they're doing. And we are not going to be expanding so much as to the why, because there are plenty of tokenizers, and explaining the why behind each one of them will actually take too much of a discussion. We will limit the discussion here to two main types, because we can actually start understanding the trade-off that exists between the two types, the sort of word and sub-word level tokenization. And that's what we're going to discuss first. So we will distinguish the discussion over here, divide the discussion here into two parts. The first is titled the word level, and the other is the sub-word. And today, we are actually pretty much here, but I think it's instructive to just discuss the simple case first, which is that of the word level tokenization. And for that, if we actually go to our site, we can actually see here an example. So let's assume I have a sentence and I have, let's say, a new GPU exclamation mark, and the tokenizer, which is very, very straightforward to actually bring in this kind of high-level APIs that are provided either by Spacey or Hugging Face. We are able to actually print each of the tokens. We have 1, 2, 3, 4, 5, 6 tokens in this kind of case, and then basically we are done. Every token is going to be further processed by our kind of pipeline, and as we will see later, the next processing stage is that of the embedding. So every token will at some point result into a vector. Okay, so however, the disadvantage of this kind of method is that it suffers from this problem of the so-called unknown words. So if we have, if you like, a tokenization model that we have developed, just like the one which is actually being used here, and in this kind of model, the specific word was never met, let's say GPU was never met, then the tokenizer will not really know what kind of token to produce out of an unknown word, and therefore we will tag that word as such, as in other words unknown. And that's obviously a suboptimal thing to do, because evidently you want all of the words to have some form of meaning later, and therefore this unknown word, if we have too many of them, then all of these words will have exactly the same unknown meaning. And so that is basically the disadvantage of word level tokenization. So if we step now into the space where we discuss the subword level tokenization, so we have in the other extreme the so-called character level tokenization, where we are solving the unknown word problem by encoding all of the words as a character, as a single character. So effectively we are going to have a pretty sizable number of tokens that are produced out of a very simple sentence, and that is actually causing the other trade-off, in a sense that the longer our sentences becomes in terms of token, then, as we have seen in an earlier video on recurrent neural networks, and this is also true in terms of transformers as well, there are going to be some far more challenges to recall the information, especially in a recurrent kind of architecture. So that is we solve one problem, but we created another. And as we've seen, gradient flow is a challenging thing to do in recurrent architectures. And that's the reason why character level tokenization, although it works, it is probably geared for small experiments, and therefore it does not have the performance of what we will end up doing, which is the so-called byte pair encoding, which is one of the many subword level tokenization approaches which we'll discuss now. To explain the byte pair encoding, as it variant of which is being used in the so-called GPT type of language models, auto-regressive language models, we have here a string, and from the get-go, I should mention that this is a compression technique that is the byte pair encoding. It was back in 1994 where it was invented. And you probably also heard other similar compression techniques such as LZ coding, and it goes as follows. So we have, let's say, the string over here, and at the very first stage, we are merging into another symbol, let's say Z, all the occurrences of the symbols that are repeating, the original symbols that are repeating. So effectively, with this first replacement, we are ended up with the string Z, A, B, D, capital Z, let's say A, B, A, C. I have chosen, if you like, a symbol to replace it that it is not really part of the string. And what we actually can do now is we can actually go and see exactly any other repetition we have here. So yet another repetition is AB and AB over there. So we will actually proceed to the second step. This is Z, maybe Y. Then we have D, Z, Y, AC. Okay, so this is basically the end result, if you like. And we can stop over here, but we could also start at a sort of second level, start replacing these now symbols with something that we have not seen before, let's say X, and that's the recursive nature of the kind of the algorithm. So this is X, D, X, A, C. And this is basically where we stop, and we have Z is equal to AA, capital Y is equal to AB, and capital X is equal to ZY. And that's how we will encode with byte pair encoding. And that was the original kind of algorithm. And if we are to see how this is kind of used in NLP, let's take a sentence. For example, let's take the sentence, she sells by the shore. Okay, so this is the input sentence, and let's see how we can just do a couple of iterations here of this kind of the byte pair encoding kind of algorithm. So we actually form, just a visual presentation of what's happening. We form a table of the original tokens, the input kind of text. So we first break this into the corresponding symbol. So each symbol corresponds to a character here. So we have, let's say, let's put the space symbol. Let's represent the space with the underscore over here. Then we have S. Then we have H, E, L, O, R, B, Y, T. Okay, these are all the input characters. And let's write next to them the frequency that we are meeting each of these kind of characters in this text. So we have 5. We have also 5 here. We have 5 S's. We have 3 H's, 5 E's, 4 L's, 1 O, 1 R. Well, everything else is 1. Okay, so the first kind of iteration is to find from all of these frequencies we have produced here. Probably we will be looking at the first top positions, probably to find the most frequent pairings that we can find in this input text. So the most frequent one turns out to be SH. So it is met over here, and over here, and over here. This is the most frequent one out of all the possibilities. So if we are to write how this sentence kind of evolved, we will be merging S and H to form now a new token that we will be appending. We will be appending this token in the original kind of list of tokens that we have. So I'm not going to write everything, but what I'm going to do is I'm going to change the frequencies because the merging will change the sentence to what? Let's see. So let's replace with Y the SH, what we decided to merge. So the new sentence is YE sells YELLS by the YORE. Okay, and so this is a sentence, but definitely the number of spaces is still 5. The S's have now been reduced to 2 over here and over here. So S is 2. H's are 0, and all the other elements are intact, except that now we have a new token, the SH with frequency 3. Okay, so this is the second iteration. And in the third iteration, what we will actually going to be doing is we're going to repeat this kind of process. We will need to find now the most frequent pairing that we can find. In this case, well, it could be that we decide to do, I'm not 100% sure if it is the most frequent one, but just for illustration purposes, let's merge the Y and the E. I can see here that there are at least 2. So we will be merging it with, so we have SH, we have, all of these tokens again. Evidently, the frequency of E will actually change. So this, let's say, this becomes Z is equal to SH and E. In fact, I should not be writing SH here. I should be writing as Y, capital YE. And then the sentence will actually be Z underscore cells underscore Z LLS by the YOR. So we have SH definitely, and then we have SHE of frequency 2. Okay, and definitely the number of SHs have actually gone down to 1, and so on. So we repeat this, if you like, this process, and then at the end of the day, we have some of these elements which are 0 are not going to be kept, obviously, so we eliminate these actually tokens, and at the end of the day we stop the process when we run out of iterations. So we have here 2 iterations. We may actually have reached the number of iterations that we pose as a parameter in the algorithm, or we reach the desired number of tokens, the maximum number of tokens that we would be able to have. And that's basically how the algorithm kind of stops, and we produce the tokens at the end. So if you go into your nodes, then you can actually see this API, how this API is sort of called with this sentence that we have actually as an example. And over here you can actually see the tokens that the algorithm has produced. So obviously the algorithm is actually is doing more pairings than what I illustrated over here, and therefore we don't have necessarily 100% agreement with all the tokens we have identified up to this point. But here's the API, and you probably noticed that some kind of weird character, this G symbol over here. This is effectively the character that is representing the space symbol, and the kind of explanation here is here for you to understand how on earth this G symbol came to be, and we don't report space. And that's basically it with respect to byte pair encoding. So the next step for us is to understand how we will be doing the embedding encoding. So we now have our tokens, and we need to our tokens now are represented in a table with some integer numbers next to each one of them. So we have now our vocabulary that has been determined from this exercise, and so these integer numbers we will see now how they are converted to a representation, a vector representation, for further processing into our kind of pipeline.